In the last video, we introduced the topic of NMR spectroscopy, a key tool in our kit of methods for determining the complete structures of organic molecules. As we continue on in this video, what we are going to focus on are chemical shifts. By the end of this video, you should be able to explain what exactly a chemical shift is and what features of a molecule are going to determine where a chemical shift resides in an NMR spectrum. So first, let's do a quick review of what we looked at in the last video, which was we looked at the concept of what creates an NMR spectrum, what creates NMR data. And that is that within nuclei that are NMR active, those nuclei will spin, and those spin states will align with the magnetic field. And I'm illustrating that here with these arrows indicating that the nuclear spin states of these three equal proton atoms, meaning three protons that are in identical environments, are going to align with the magnetic field. So I have all those arrows in the same direction. Those will be subject to a range of frequencies of electromagnetic radiation, which I abbreviate as EMR here for electromagnetic radiation. When a certain specific resonance frequency is reached, what will happen is those spin states will flip. And I'm illustrating that by showing the arrows rather than pointing upward, now pointing downward to illustrate that they have experienced that flipping of spin states. And that resonance frequency is detectable. The specific value of that resonance frequency is dependent upon what we refer to as the chemical environment of that particular nucleus. And when we say the chemical environment of that particular nucleus, what we are referring to is what atoms or functional groups surround the particular nucleus that we're detecting. And we're going to look at proton NMR as our example here. So we're going to say the atoms or groups surrounding the proton that is being detected. So the exact resonance frequency of a particular proton is dependent upon what functional groups are surrounding it. And so in other words, if we were looking at a structure like this, say, of an alcohol, ethanol, what we would find is that the chemical environment of the proton that is part of the hydroxy group that I drew the blue arrow to here in your upper right corner, the chemical environment of that proton is different than the chemical environment of the two CH2 protons. And the chemical environment of those CH2 protons are different than the chemical environment of the methyl group protons here at the terminal end, because in each case, the exact nature of the atoms that are nearby, either bonded or a couple of bonds away, are different in each case. So the proton here of the hydroxy group directly bonded to an oxygen, that puts it in a different chemical environment than the chemical environment that is shared by these two hydrogens of the CH2 group, where both of those are directly connected to a carbon, and then one additional bond over from a methyl group, one additional bond over from a hydroxy group, etc. And then a third chemical environment is over here with the three hydrogens that are present as part of the methyl group, where all three of those hydrogens are one bond away from a carbon, two bonds away from a CH2 group, three bonds away from the hydroxy group. And so as a result, each of those three hydrogen sets that I have highlighted here are in three different chemical environments, and hence they have three different resonance frequencies, because the exact resonance frequency depends upon the exact chemical environment of the particular nucleus. And nuclei that are in exactly the same chemical environment, such as all three of these hydrogens that are directly bonded to the carbon and the methyl group, are going to have the same chemical environment. And so what this gives rise to is what we refer to as the chemical shift. The chemical environment of a particular proton is going to determine its chemical shift, the position of the signal on the x-axis in an NMR spectrum. So let's take a look at dissecting an example NMR spectrum and discuss some of the terminology that we need to be able to apply to determine the chemical shift values. So I will draw out here a Proton Nmr Spectrum schematic. So I'm drawing my x-axis here, and on the x-axis, generally the scaling is done from 0 to about 14, and we refer to this x-axis as the chemical shift. the chemical shift is abbreviated as a delta value, and the units that are applied to this are parts per million, where we are referring to the difference in value between a standard that we establish at 0 ppms and going from there toward 14 as about the largest typical ppm value that we see for chemical shifts in protons that are found within organic molecules. So this is our Proton Nmr spectrum. And along that x-axis, what you will see popping up along the x-axis are a variety of signals or peaks showing up along this axis. So in this particular Proton Nmr spectrum, what I am showing are 3 different signals, one here, and one here. These refer to 3 different chemical shifts. So 3 signals that we see in the spectrum. In other words, corresponding to 3 chemical shifts means there are 3 different chemical environments that protons reside in within this molecule. So when we are thinking about the importance of chemical shift in determining the structure of an organic molecule, we can think about what the chemical shift values are useful for in terms of starting to understand the structure of a molecule. One of those uses is determining the number of types of different protons. And when we say that protons are different, we're referring to how many non-equivalent protons there are within the molecule. Non-equivalent protons are ones that have different chemical environments, meaning that they are bonded to different types of atoms, placing them in different regions of electron donating groups or electron withdrawing groups within the molecule. So, for example, if we were to look at diethyl ether, this molecule here, I could ask you, how many different signals would we expect to see in a Proton Nmr spectrum for this molecule? And the number of different signals will correspond to the number of different environments that we expect to observe protons within. So when we look at this molecule, at the terminal ends here, we have a CH3 group here in pink and another one in pink that I'm highlighting, those 2 terminal ends. Those are totally symmetrical, completely symmetrical within the molecule, and hence those 2 sets of protons are in the exact same chemical environment. And since they are in the same environment, they're going to give one signal within the NMR spectrum. There are a total of 6 protons that would comprise that one signal, because you have a CH3 group here, a CH3 group here, since those are totally symmetrical in the molecule, meaning they are both directly connected to a CH2 group, and that CH2 group in both cases are directly connected to an oxygen and so on. Those are going to be exactly the same chemical environment, meaning they're exactly bonded to the same number and type of atoms, resulting in them being seen as one signal. Then we take a look at the CH2 group here and here that I'm highlighting in blue. Those are also in the same exact chemical environment as one another, and so they are going to show up also as their own signal. And hence, the total number of signals that we would expect to see in a Proton Nmr spectrum for diethyl ether is 2, because there are 2 different chemical environments. So the chemical shift, the number of signals that we see in the spectrum, is going to reflect how many different chemical environments there are. In other words, how many different types of protons are there within the molecule, where we would say that all 6 of these protons that make up the 2 methyl groups are in exactly the same environment. Those are all equivalent protons. Equivalent protons are ones that give the exact same chemical shift because they're in the same chemical environment. Different protons or non-equivalent protons are going to give different chemical shifts from one another. And so that's one piece of information that we can glean from an NMR spectrum, is the number of different types of protons, the number of different chemical environments that the protons reside in. The other important piece of information that we can glean from a Proton NMR spectrum is we can gain information about the types of groups that surround the proton that we are observing in the spectrum. And the types of groups that are surrounding the proton that we're observing in the spectrum are going to be defined as electron donating or electron withdrawing groups, which are going to determine how far to the left, meaning closer to 14, versus how far to the right, meaning closer to 0, a particular proton signal is, where the general trend is that as we go toward the left, closer to 14 in the spectrum, that indicates that there are increasing electron withdrawing groups surrounding the proton that we're measuring the chemical shift of. Whereas if we go the other direction, there are decreased electron withdrawing groups, and instead, there will generally be electron donating groups. And we go back to Org 1 when we think about electron withdrawing versus electron donating groups, where electron withdrawing groups are typically electronegative atoms nearby that can withdraw electrons by induction, by bond polarization and pulling electrons away from them. So for example, if you have an oxygen nearby in the molecule, the oxygen is electronegative, so it's pulling electron density away from the proton and toward itself. On the other hand, the typical electron donating group by induction is an alkyl group, which is going to push electron density away from itself and toward the rest of the molecule. So we define that as an electron donating group. And so what will happen is that when there are electron withdrawing groups in the vicinity, those are going to do what we refer to as de-shielding the proton that we're measuring. And we say that the proton is de-shielded. What we mean is that the proton that is being measured is in a region of low electron density. And the reason that a region of low electron density creates this so-called de-shielding effect is that electrons tend to blanket or shield the nucleus from the effects of the magnetic field that they are placed in. And so when there are electron withdrawing groups nearby, the proton that we are measuring doesn't have an electron blanket to shield it. And so therefore it is de-shielded, and that forces the signal to be further to the left, meaning in this de-shield environment, meaning closer to 14. The other term we use to describe protons that are de-shielded is we describe them as being downfield in the Proton Nmr spectrum. On the flip side, in regions of high electron density where there are electron donating groups nearby, we describe those protons as being shielded, and shielded protons are what we refer to as being upfield. The terms upfield and downfield, shielded and de-shielded, don't refer to specific numerical values within the spectrum. Instead, they are relative values, where if we see a signal that is closer to 14, such as this one that I'm highlighting with my laser pointer, we would say that that signal is downfield relative to all the other signals within the spectrum. Or if we look here, closer to 0, the signal that I'm circling now, we would describe as being the most upfield or most shielded signal within the NMR spectrum. And so we can glean information about the environment of each proton by looking at where it resides along the x-axis, inferring that signals that are further downfield are in regions of low electron density because they're near electron withdrawing groups, whereas protons that are in regions of high electron density are going to be more upfield. And due to the fact that NMR has been around quite a while, empirical values have been determined for common functional groups and where we expect the chemical shifts to occur along this x-axis range. And so if you take a look at the handout that corresponds to Chapter 13, you will find a chart of expected proton NMR chemical shifts that go along with common classes of organic molecules. So let's take a look at that. You do not need to memorize any values from this particular chemical shift chart because you have access to this in your handout and you can pull that up when you are taking quizzes and things like that. And in this chart, the pink bands show the expected chemical shift range of a particular proton. So for example, at the very top of the chart, we see that the hydrogen atom here of an alcohol group is explicitly shown there at the top. And what we see is that its expected chemical shift range is from about 6 ppm at the very downfield end of that range, all the way upfield to about 0.5 ppm. And the reason that range is so broad is because of the fact that that proton is capable of hydrogen bonding. And we can continue to interpret this chart by looking at some other protons. Keep in mind throughout the chart that the proton in focus, the proton that we are looking at the specific chemical shift range of, is the proton that is shown explicitly. So for example, right here toward the middle of the chart, I'm highlighting a proton that is what we call a vinyl proton, a proton that is directly bonded to the alkene carbon. We would expect to show up in the chemical shift region of about 5.75 to approximately 5 here, because that's where the pink band is that shows up adjacent to it. We can also look at other protons. For example, if we have a methyl group, the CH3 group protons that are bonded to an alkyl group, because the R group is defined as an alkyl group there in the upper left-hand corner of the chart, we expect that to show up at around 1 ppm. So that's very shielded due to the fact that that is an alkyl group. So we just have carbons surrounded by other carbons that are electron donated. If we go very downfield, we come to some very d-shielded groups, such as the aldehyde proton, right here showing up at around 10 ppm as the expected range of that, and the carboxylic acid hydroxy group proton showing up very downfield from 10 to out all the way to 13 or so ppms, very, very d-shielded. And the reason that proton is d-shielded is due both to the fact that the oxygen atoms here are electron withdrawing by induction, and then by resonance we can also pull electrons away from that proton by moving the pi bond electrons up onto the oxygen. If we move those pi bond electrons up onto the oxygen, that is moving electron density away from this proton, and hence making that an electron withdrawing group by resonance and induction. So that makes this group very, very d-shielded, more so than any of the other functional groups that we are looking at. Another key factor or feature that you should be aware of is that the ARH abbreviation here, the AR, throws a lot of people off. That refers to an aryl group, where an aryl group is an aromatic ring. So it's that 6-membered ring that has alternating single bonds and double bonds, and by resonance, that is a very electron withdrawing group, and hence the protons that are directly bonded to the aromatic ring are in a very d-shielded environment, because that resonance that's going on within this ring is pulling electron density away from that proton and hence de-shielding it and causing that signal to show up somewhere between about 6.5 and about 8.5 ppms. Keep in mind that if you have multiple functional groups coming into play, that they can cause the chemical shift values to change a bit. So for example, if we have a CH2 group that we are seeing up here toward the top of the chart, our CH2 group that's directly bonded to a Cl, we expect to show up somewhere between about 3.25 and about 3.75. But if we had 2 chlorine atoms here instead of 1, having 2 chlorine atoms there is going to push this signal further downfield, because the presence of those 2 chlorine atoms is going to create an environment that is more de-shielding. So you have to apply this chart in combination with your logical understanding of electron donating and electron withdrawing groups, keeping in mind that the effects of electron withdrawing groups in particular are cumulative. So if you have 2 different electron withdrawing groups nearby a particular proton, that signal is going to be more de-shielded than would be shown by the chart, which indicates just that there's 1 chlorine or whatever electron withdrawing group we are talking about. So this chart is going to be extremely useful to you when we get to the point of interpreting NMR data, because it will allow you to take an NMR spectrum and look at a particular chemical shift value that you are seeing. And when you see that particular chemical shift value, you'll be able to look at this chart and go, okay, what are the hypothesized functional groups that may correspond to that chemical shift that is at a particular ppm range? So for example, if you saw a chemical shift at 5.5 ppms in your spectrum, you could look right here at 5.5 and go, okay, I hypothesize there is an alkene group in the molecule, with that proton being the one that's directly bonded to the alkene, or maybe a hydroxy group, and we're looking at the proton from that hydroxy group to make hypotheses about the groups that you see within a molecule. So this will be one of the pieces of information that is useful that you can glean from an NMR spectrum, is the chemical shift In the next two videos, we are going to look at other information that you can glean from an NMR spectrum. Those other two pieces of information are multiplicity and integrals, meaning by integral, how big is the signal? By multiplicity, we mean how many of those little subpeaks are each signal split